In this video, you will efficiently model recycles and looped processes. In addition, you will define and implement performance curves to more accurately represent rotating equipment. In this video simulation, feed gas enters a compressor station at about 1725 kPa and is to be delivered at 6900 kPa after two compression stages. Each stage consists of a compressor model, aftercooler, and knockout drum. Liquids from each separator are recycled back to the previous stage after the pressure has been reduced. This video includes the following tasks: build the flow sheet, install recycles, add the compressor curves. Now to our first task, build the flow sheet. Start a new hysys case. Add a new component list. Add nitrogen, carbon dioxide, methane, ethane, propane, isobutane, normal butane, isopentane, normal pentane, and normal hexane to the component list. Now select the fluid package. Add a new fluid package and select pink repulsor. Now we are ready to move to the simulation environment. Add a new material stream to define the feed. Change the stream name to compression. Set a temperature of 35 degrees centigrade. And set pressure of 1724 kilopascal. Set the molar flow to 4990. Now to the composition. Enter the following composition. Now the stream is fully defined. Let's add a mixer. Set the outlet stream to compression and change the automatic pressure assignment option to equalize all. And don't forget to name the outlet stream. Now the mixer as well fully defined. Now let's add a separator. The outlet stream will be the stream coming from the mixer, and we have the liquid outlet and the gas outlet. The gas outlet will be the feed of the compressor. Let's add a compressor. Name the energy stream and the outlet stream and set the adiabatic efficiency to 75. And on the worksheet tab, set the pressure of stage 1 outstream to 3447. Now install a cooler to cool down the outlet stream of the first stage of compression. Set the outlet stream and name the outlet stream and the energy stream. On the parameter page, set the pressure drop of 0, and on the worksheet tab, set the temperature of the cooler 1 outstream to 50 degrees centigrade. Now let's add another mixer and separator, as we did in mixer 1. On the parameter page, set the automatic pressure assignment to equalize all options. Now we will add a valve. This valve will act as a let-down station for the liquid outlet stream from the knockout drum of the first stage in order to be ready to be sent as a feed to the first stage, as we will do in the next task. On the worksheet of let down station, set the outlet pressure of 1724. Now let's add the second stage compressor. We added the same unit operation used in the first stage: a compressor, a cooler, a mixer, and separator. The only difference will be the pressure values. In the compressor, set adiabatic efficiency 75, and on the worksheet tab, set the outlet pressure as 6095. For the cooler, set the outlet temperature of 50 and pressure drop of 0. Finally, on the let down station number 2, set the outlet pressure of 3447. This concludes the first task in this video. Let's move to the next task. Task 2. Install recycles. The recycle operation allows aspen hysys to solve two recycle flow sheets. A set of conditions are assumed and used to solve the recycle loop. The assumed values are compared with the calculated values computed on the next iteration and updated. This repeated until the values match within a specified tolerance. Please note, recycles are sometimes also called as tiers. Add the first recycle loop. Set the inlet stream to the let down station outlet. After the recycle operation has solved, the inlet and outlet streams will match each other within certain tolerances. Aspen hysys allows the user to set these tolerances to match the requirements of their simulation. The actual tolerance of the recycle operation is calculated as the product of the initial tolerance for the given property, which are fixed values within aspen hysys, and a sensitivity value which is specified by the user. Whether the tolerance used is an absolute or relative tolerance is dependent on the specific property in question, and it's set by the aspen hysys program. The following table gives the internal tolerance for each property. While the internal tolerances are set within the program, the user determines the actual tolerances by specifying a scaling factor called sensitivity for each variable. The default sensitivity for all recycled properties is 10, which aspen hysys generates automatically. You are able to modify this sensitivity if desired. Remember, however, the smaller tolerance will require more calculation time. If your simulation contains streams with very low ppm concentration, you may want to set the concentration tolerance to a lower value. Otherwise, the default tolerance works well in most applications. Please note that checking the use component sensitivities checkbox on the parameter page allows different tolerances to be used for each component. The numerical page contains the option for the two types of the recycle convergence calculation: nested and simultaneous. Nested recycle is best applied if there is a single recycle or if there is multiple recycles which are independent from each other. Simultaneous recycles are best used if the flow sheet has multiple interconnected or overlapping recycles. When recycling operations are selected as simultaneous, they will not be calculated with the other unit operations. Instead, they are listed in a separate solver and calculated only after the ordinary solver has finished calculating all other unit operations in the flow sheet. Please note that due to process simplicity, we can use the default nested option, even though this case has interconnected recycles. In fact, oftentimes the default nested option works just fine for any combination of recycles you may need to test both approaches. The recycle operation can be set to use one of two types of mathematical algorithm in order to reach a convergent solution. The two available acceleration methods are Wettstein acceleration and dominant eigenvalue acceleration. There are several numerical parameters that define the operation of Wettstein acceleration. These parameters are acceleration frequency, the number of iterations per number of accelerations. Q max, set the maximum value for Q in Wettstein equation. Q minimum, set the minimum value for Q in Wettstein equation. Acceleration delay, the number of iterations before the first acceleration is applied. The Wettstein equation is used to determine the value passed to the outlet stream for each accelerated iteration. X is the value of the outlet stream assumed. Y is the value in the inlet stream calculated. N is the number of iteration number. And Q is the acceleration factor. Aspen hysys chooses the value of Q that it will be depending on the amount of change that has occurred between successive iterations. A larger value of Q will be used when the change between successive iterations is large, and vice versa. While Wettstein acceleration has been shown to reduce the number of iterations needed to converge a recycle operation in most cases, there are a few cases in which the default Wettstein parameters will not help to converge the recycle operation. In these cases, it is necessary to reduce the amount of acceleration or to ignore it altogether. Very rarely, the recycle operation will escalate as it converges on a solution. If you find this happening in your simulation, you can increase the value of Qmax to a small positive value. This will provide a damping effect that will helpfully reduce the oscillating behavior. The dominant eigenvalue acceleration method is less adjustable than the Wettstein method. It is recommended for recycled operations in systems that are non-ideal and where strong interactions exist between the components. This method has the advantage of examining the interaction between the variables during the acceleration process. Please note that the progress of the calculation performed by the recycle operation can be checked on the monitor page. This is useful if the recycle is having problems converging. Now let's add a second recycle operation. Set the inlet stream as the outlet of the second letdown station. Name the outlet stream. The final step to solving the flow sheet is to connect the recycle outlets as inlets to mixer 1 and mixer 2. Then the flow sheet will begin solving. Attach recycle 1 outlet as inlet to mixer 1. And attach recycle 2 outlet as inlet to mixer 2. The entire flow sheet had converged at this point. Look back at recycle 1 operation. Change the sensitivity of composition to 1. Since in task 1, both mixer 1 and mixer 2 were set to equalize all as the automatic pressure assignment. The pressure of recycle 1 and recycle 2 can be deleted if the transfer direction of the pressure is set to backwards. This concludes task 2 in this video. Let's move to task 3. Add the compressor curves. Compressor performance curves allow you to calculate hydraulic head and efficiency as a function of flow ratio into the compressor. Using compressor curves in your aspen hysys simulation allows you to model existing or potential plant equipment. In this task, you will investigate a set of compressor curves which have varying operating speed, allowing the compressor to change its speed to meet demand. You will install these curves into the stage 2 compressor. In the property view of stage 2 compressor, navigate to the design tab and the parameter page. Delete the adiabatic efficiency. Ensure that both adiabatic and polytropic efficiency boxes both read empty. Please note that these values will be calculated based on the compressor curve, and defining an input value in two places will always result in a consistency error. The compressor performance curves you will be provided in this task are defined in metric SI units. The entry of the curve data goes much more smoothly if the simulation unit set agrees with the unit of the curve data. That being said, it's advised to select a matching unit set for the flow sheet. Move to the rating tab of stage 2 compressor. On the curves page, ensure that adiabatic efficiency is selected. Click Add Curve. Set the speed to 5000 RPM. The performance and efficiency data for this speed and other curves can be found in the following table. Please make sure you use the correct units for all the curve table variables, and that you set the unit before entering the curve data. To guarantee proper units and data, set the default simulation units to the SI set while entering the curve data. This will maintain consistency between the SI input data from the table and the SI preferences in the curve input. Continue by adding 3 more curves to your stage 2 compressor by adding the data for the 7000 RPM, 9000 RPM, and 11,000 RPM curves. Activate the individual curves by putting a check mark next to each speed curve. Finally, select the Enable Curves checkbox and the compressor should calculate. The compressor speed is 10,500 RPM. You have the option to plot the compressor curves. You can also check the different parameters of the compressor on the Performance tab. The compressor adiabatic efficiency is 71.8 and the polytropic efficiency is 73.5. This concludes our video. Thank you for watching.